Welcome everybody to this seminar of Forum Numerica. It's my pleasure to introduce to today's speaker, Andrea CLEMENTI. He's a professor at the University of Rome, Tor Vergata. He got his PhD from University of Sapienza and then held position at UC San Diego, at the University of Geneva, and also here in Sophia Antipolis, right?
Just visiting.
Visiting for several months, right? And he's an expert on randomized algorithms, on distributed computing and other areas of the theory of algorithms. And in particular, in the last decades, he worked a lot on exploring some class of algorithms and processes that can be grouped under the name of opinion dynamics, which are of interest in sociology and other fields. And this, in this research direction, he produced results that have been well perceived by the algorithm community in the major venues in the theory of algorithm. And today, this is going to be the main subject of his talk. So, Andrea, it's my pleasure to leave you the floor.
Thank you, Emanuele, for this nice introduction. And I would like to thank the University Côte d'Azur and INRIA for inviting me in this nice and beautiful place. So let me first just introduce the research team. I had the pleasure to work for almost 2 decades. The senior group is this list of professors. I just highlight my first PhD student. One of them is Emanuele, and also some PhD and postdoc students that have some French connections. So, and in particular Francesco D'Amore, which was a PhD at INRIA with Emanuele, and then Giacomo Scornavacca, which was visiting already here, and Robin Bacchus, that is now I know that has now gotten a position at CNRS, and Isabella Ziccardi, that is a postdoc at Paris 7. Okay, so today I would like to describe, to give an overview of one of our line of research on dynamics and distributed systems. In particular, we know that distributed systems are pervasive in our digital and real lives. We can see them in fields like biological population systems and of communication networks like peer-to-peer networks, opportunistic networks, and so on. The theory of distributed computing provides an approach, an algorithmic approach to study such distributed systems, and this algorithmic approach is typically known with the name given by Karp in 2011, which is called computational lens. Just to give an intuition of how this, which is the language of this approach, if we see how works distributed systems, we have from a local point of view on this local side. On the local side, we adopt the language of computational physics and statistical mechanics. We have particles that interact via simple interaction over maybe an Euclidean space. And if we look at from the top level, from a global level, such interaction generates what is called a complex behavior, maybe threshold phenomenon and self-organization. If we adopt the computational lens, what's happened is that particles become agents or nodes of a communication graph that can be dynamics, and the simple interaction in the computational language, in the algorithmic language, becomes algorithmic rules that allows to change states, so agents have computational power and memory to make local computation. And such algorithmic rules are designed to compute a task, a global task, or to solve a given problem. So what we observe in terms of computational physics, self-organizing behavior, in the computational algorithmic approach, we mean the fact that the systems is able to solve some non-trivial computational problem. Okay, so just to be more concrete, we give 2 examples. We have that the global task is broadcast, so we have one node of the system that initially has a piece of information. This node is called the source node. And we want a simple protocol that is able to perform the broadcast. This means that we want that all nodes get the information that initially was only in the source node. So, for instance, the flooding works in this way. Initially, we have this configuration for a graph, so only the source node is informed, so it's a red one. Then the local flooding says to the source to send the message to all its neighbors. And so after the first step, we have the two neighbors that are informed. Then every informed node send the message to all its neighbors. So after 3 steps, we reach the final configuration which all nodes are informed. So the local protocol is the flooding, and the global task is the broadcast one. Another situation like this is when the task is the global consensus and the local algorithmic rule is the majority rule. Here we have an initial configuration which every node can support 2 opinions, maybe red and blue. And the global goal is to reach a consensus, so a configuration monochromatic configuration in which all nodes supports the same color. And the color must be legal, so that color must be present must be supported by at least one node in the starting configuration. So the majority rule, the local majority rule, how it works, every node look at the color of its neighbors and apply the majority, including itself. If there is a tie, then keep its color. So after one step, we see that, for instance, the top node on the left gets the color blue because the majority of its neighbor is red, and so on. And so again, after 3 steps, this graph is small, so we are lucky to display. We reach the monochromatic configuration which all nodes supports the blue nodes. And typically, the distributed computing theory try to understand whether, starting from any configuration, the system, the majority rule, can reach a consensus, and how many time steps are required to get this monochromatic configuration. Okay? Okay, so we have made 2 simple examples, and so we are able to introduce the first important ingredient of our line of research, and are dynamics. Dynamics are exactly local algorithmic rules that are very elementary, very simple. Because the function that says which is the next state of the nodes, must be invariant with respect to time, to network topology, and to the identity of the nodes. Just to make more concrete, the time clock cannot be a variable of this function, and the network topology, if you are on a hypercube or in a butterfly or whatever you are, the function is always the same. And for instance, if you are on the internet network, you cannot use the IP protocol, the IP address to make a different rule. Okay? So dynamics are extremely simple, and so the only arguments are the node's current state and those of its neighbor. So flooding and majority are typical example, well-studied example of dynamics. Okay? To consider a more general scenario, so we have this list of dynamics for the broadcast task, flooding, rumor spreading, which are also called push and pull, and we will see them later. Epidemic models. Epidemic models are typically adopted in mathematical epidemiology to model the spread of infections over a social network. And for consensus, we have the well-known voter model, the median, majority, and the undecided state protocol. While for a quite more complex task, which is the community detection, in the literature, dynamics that have been introduced to solve this non-trivial task that are considered are the averaging dynamic, again the majority, and some label propagation algorithms. Okay, so but the role of dynamics does not apply only on the node rule, okay? But also dynamics are also adopted to generate a reasonable process that make the communication, the supporting communication graph evolve over time. So dynamics are used also to make the communication graph change over time, okay? And there are two kinds of graph dynamics: link-based dynamics, in which the dynamics exactly determines the behavior of every edge, maybe according to some probabilistic rule. Here we have some example. In particular, edge Markovian evolving graph will be described later, or adversarial graph, in which there is an adversary that tries to change the state of every edges directly in order to make a worst-case situation for the protocol. Or there are also node-based graph dynamics, in which the dynamics control not directly the topology of the graph, but the behavior of the nodes. So assume, for instance, that we have nodes that represent mobile devices over a metric space. So nodes moves around according to some trajectory, maybe random. And as a consequence of such behavior, of such dynamics, the communication graph, the topology of the communication graph changes over time. Okay, so we have two kinds of dynamics. So the term dynamics in my talk will have two different roles: the algorithmic rules that every node applies during the protocol, and the local algorithm, and the dynamics that generates the communication graph that evolves over time. Okay. Okay, so motivations about this, we would like to analyze what is called, the phenomenon what is called the emergence of complexity from simplicity. Simplicity is the fact that such dynamics are extremely simple and natural and local. And complexity means that if you see the whole systems, the system is able to compute some non-trivial global task, or to solve some non-trivial global computational problem. Okay? We have two main reasons. We would like to understand the process, the behavior of the system, and maybe to predict important network phenomena like threshold phenomena or the outbreak of an epidemic, using a rigorous analytical approach. And on the other hand, we would like to exploit some rigorous analytical approach to get some interesting idea to design efficient distributed algorithms to solve the problems. In the first case, the dynamics is there and we just want to observe what is going on. In the second case, we would like to design simple dynamics that are able to solve a specific task like shortest path computation and distributed community detection. Okay. I can give only a very short and rough summary of what was the state of the art before 2008. Then on the one hand, there was a rich and effective set of results and methods for dynamics when the graph, the communication graph, is static, so never change during all the process. While as for the case in which the communication graph evolves over time, we only had sporadic results that have no structural results. Okay, so we started this journey, this line of research for almost 2 decades, and indeed we considered the flooding dynamics in a family of dynamic graphs, and we then gradually moves to different dynamics and different graph dynamics. And despite our trajectory seems like a random walk, but what we can observe is a trend, and we in fact consider a modular approach that clearly moves towards more complex framework. In particular, we consider simple cases, and starting from a simple case, we add some concrete features arising from realistic scenarios. And a way to describe this trajectory, we can consider two key aspects of the considered models. The first one is the graph dynamics that we adopted together with the communication model, and the agent dynamics that we adopted in the systems. So if we consider graph dynamics, we started with simple model, and then we add concrete features like node mobility and node charm. Node mobility, I think anything can get an intuition. Node charm means that not only the topology, I mean the edge set change over time, but also the node set change over time. So new node can join the network, and some old node can leave the network. Okay? And as for information dynamics, so the agent dynamics, we started with the very simple dynamics like flooding, and then moved to more complex dynamics that are able to solve more complex global task. Okay? In this talk, I will focus on the broadcast task and over evolving graphs. And this is the path, the trajectory of our research. I just give some highlights of this figure. We start, as I said, by studying the flooding process, the flooding dynamics over an evolving graph in which any edges follows a simple Markovian chain. So there is the first model in which time stochastic dependence has been introduced. Then if we move with respect to the x-axis, we keep the flooding dynamics, but we introduce some more concrete and realistic aspects of such evolving graphs, and making things quite harder. So in the first model, edge Markovian evolving graph, there is no spatial dependence among edges of the same snapshot, of the same graph at the same time. Then we introduce random node mobility, and so we introduce a node spatial dependence in this study in 2009, flooding over geometric Markovian evolving graph. Then we improve this analysis by considering trajectories that are much more realistic, like Manhattan random waypoint, and then finally consider very general cases of Markovian evolving graph. And finally, after 10 years, more or less 10 years, we go back to flooding, but for the first time we consider the case in which, as I said, a node can join and leave the network at any time. If we move towards the y-axis, then maybe we consider the edge Markovian evolving graph, but instead of flooding, we consider a much more communication efficient protocol, which is the push-pull protocol, in which every node does not send the message to all nodes, but just maybe chooses one random node and send the message only to this. And this is a very important and well-studied protocol, which falls in the class of rumor spreading protocols. Parsimonious flooding instead is something that in which an informed node can send the message to all its neighbors, but only for a few times. So once a node is informed, maybe for the next 3 steps is active and can send the message, but then it's stopped and put in the quiescent state. Of course, if the graph is static, this does not change the things with respect to the classic flooding. But if the graph evolves over time, like the geometric Markovian evolving graph, this makes a big difference both in the results and in the analysis. Then in the 22, maybe inspired by the tragic, dramatic situation of COVID, we consider the epidemic models like susceptible, infected, recovered dynamics, in which a node gets the information and with some probability can transmit the virus, the information, to one of its neighbors. And, but after a while, with some probabilistic rule, get recovered and goes in the infected states. And we study this particular dynamics over models of small word graphs. Okay? Okay, so this is the picture only for the broadcast. Then I don't have time to discuss other scenarios, but I just want to mention that similar trend we experienced for the community detection, distributed community detection. And since this line of research started when Emanuele was one of my master's students, and actually we initiated this research with him, and he played a key role in this study. Maybe Emanuele sometimes can give a talk in the future for this line of research. Okay, so my talk will focus on dynamics for broadcast, and in particular I will refer to such two contributions. First, I will discuss the results on the edge Markovian evolving graph, and then I will move on the introduction on geometry on this model, and so on the node mobility. Okay, so the first part is flooding in edge Markovian evolving graph. What is an evolving graph? We have a static set of vertices, so of node agents, of n nodes, while the set of edges is a function of the time. So assume that times are discrete, so we have time steps. And so an evolving graph is an infinite sequence of pairs VET, where ET is the snapshot, so is the topology of the graph at time t. Okay? And we can give a formal definition of broadcast. So the broadcast in an evolving graph, initially we have only one source node S that want to send a message M to all nodes, and a node is informed at round T if it is either the source node or it has received the message at some previous round. Okay? So now we can define formally the flooding algorithm. At every time steps, every informed node send a message to all its neighbor in the snapshot GT VET. Okay? This makes a lot of difference, the fact that the nodes perform this action at every time step. Okay? So not only once, because the evolving graph changed the topology, and so nodes must keep sending the message for all the rest of their life. Okay, the flooding time is quite natural to define. Assume that the source gets informed at time t equals 0, then the flooding time of the evolving graph of G is the number of time steps required to inform all nodes in V. Clearly, in some cases, this number can be infinite. Okay? And also, if G is a random process, then of course the flooding time is a random variable over the distribution of this evolving graph. Okay, so why flooding? Well, flooding is clearly the fastest protocol for flooding. So is and sometimes in some anonymous and critical situation is the only protocol that nodes can apply. And it's also a natural lower bound. So if you have an idea of a more communication efficient protocol, you can always compare the performance, the time, the compression time with the flooding time. And also an important aspect, an important remark is that in evolving graph, the notion of diameter has an important role because you can construct an evolving graph that has always diameter 2, but the flooding time may be linear, maybe n. While you can even construct another evolving graph, another dynamic graph, in which at every time the snapshot is always disconnected, so the diameter is infinite, but the broadcast time is log n. So diameter has no an important role in dynamic graphs, while flooding time is exactly the lower bound that you should take in consideration when you compare the efficiency, the convergence time of other protocols. Okay? Okay, so as for random evolving graphs, before 2008, the analytical results that were available for flooding time was dynamic graphs in which there was fully spatial and temporal independence. So the existence of an edge at any given time does not depend on the existence of other edges and does not depend on the topology of the previous steps. So our goal was to introduce stochastic time dependency. We wanted that the state on-off of an edge at time t depends on the state of the previous section, of its state in the previous step, and we would like to provide analytical bounds on the flooding time. Okay, so I would like to highlight how we introduce this using a modular approach. So in the static case, the most popular model is the Erdős-Rényi random graph, and it's extremely simple. We have a parameter p, we have n nodes, we have a parameter p, and so for any pair of vertices, we flip a coin, and with probability p, we put the edges, and with probability 1 minus p, we don't put the edges. So edges are fully independent, and we have a random graph, okay? And we have, for Erdős-Rényi graph, random graph, we have a lot of results. We only consider these properties because we can compare our results with these kind of results. Then we have a threshold behavior. We have a connectivity threshold. In fact, if P is something like log n over n, then what we can prove is that the random graph G is without probability connected and has logarithmic diameter, and the expected node degree is logarithmic. Okay? If P is smaller than 1 over n, then G is without probability formed by very small connected component, so that is fully disconnected. Okay, sparse and fully disconnected. What's happened between log n over n and 1 over n is something that is not interesting for the sake of our talk. Okay, so let's neglect this discussion. Okay, so you know that if P is larger than log n over n, we have a good connectivity, a good fault tolerance, while if P is under 1 over n, we have a very sparse graph and very disconnected graph. Okay, so let's make this graph static, let's make it dynamic. And the first simplest idea is to sample at every time a new random graph with Erdős parameter P. Okay, so at the beginning we sample a graph according to this distribution. We have the graph, we apply flooding, then in the second round we completely forget the topology at the previous step, and we flip again another graph according to the same distribution, according to the same GNP. But we see that some nodes will be informed and some other are still not informed, so we have to follow this process of the flooding process. And as you may consider, there is full independence between the topology at time t and what is the story, the history, the trajectory, the previous trajectory. Okay? Okay. Okay, so what we were inspired by the well-known reciprocity graph model introduced by Wasserman in the 80s in social networks. And we would like to implement this simple paradigm. So we want that the state of the edge at time t should stochastically depend on its state at time t minus 1. Okay? So we consider the following simple Markov chain. If at any given time t minus 1 the edge were present in the topology, then it will die, it will be removed with probability q. While if the edge was not present in the topology at time, in the snapshot at time t minus 1, we flip a coin and with probability p we put the edge. And this operation is made to all possible pairs of nodes independently each other. Okay? So q is the edge date rate and p is the edge birth rate. Okay? So we have an infinite sequence of snapshot of random graph, and the topology at one time stochastically depend on the topology of previous time. Okay? So this is the simple two-state Markov chain, that the birth date Markov chain that generates the sequence of yes, no of every edge. Okay? So 0 is the no state, and with probability p the edge comes into existence, and if the edge was in the state 1, with probability q will die. Okay? So there is independence among edges on the same snapshot, but there is Markov dependence in the time sequence of the state of every edge. Okay? And what we can say is, okay, this is a Markov process and is a Markov chain, and what we can prove is that if p and q are not 0 or 1, the process, the dynamic process, the graph process always converge to a stationary distribution, and which is the stationary distribution, is again an Erdős-Rényi random graph, but with a different p. So this is capital P, and the probability that an edge exists in this stationary distribution is this simple formula, is p over p plus q, and of course the probability that edge does not exist in the stationary distribution is q over p plus q. If you sum up, you get 1. Okay? Okay, so if we look at the stationary graph, we have that the stationary graph has this expected degree, and let's look, so is n times something like n times p over p plus q, and let's look at these two simple cases. Assume p is something like k over n, where k is an absolute constant, so we have some order of 1 over n for p, and q we set 1 over 2. You can put any constant there and nothing change. So in expectation, you have a topology, you have a set of edges that existed at time t minus 1, then a constant fraction of these edges will die. Okay? In this case, what we can prove is that in the stationary distribution, the expected degree is k. So if k is an absolute constant, you have a sparse and disconnected graph. Okay? Because we are under the threshold connectivity. While if we set p equal again k over n, like the first case, but q is not constant but follows the same rule, so it's something like k over n, okay? In this case, the situation dramatically changed, because what we see is that the expected degree of the stationary graph is linear. So we get an almost complete graph. So it's extremely dense and well connected. Okay? So what we can see by looking at these two extremal cases, that Q seems to play a very crucial role. If Q is 1/2, we have a sparse graph. If Q is something like 1 over n, we have an almost complete graph. Okay? But in what we were able to prove is the following. If we were able to determine an almost tight bound on flooding time for any values of p and q and for any choice of the initial topology. Okay? And this is an explicit function, and this flooding time is theta of this function, which depends on n, p, and q. And this happens, and what we were able that this result does not only in expectation, but also in concentration. So this happens with high probability for any choice of the initial topology. This function is the following, is log n over log of 1 plus n over p, okay? And so we have the first k consequence. Look at the formula, q does not appear. So even though here seems to play a crucial role, as for the flooding time, we have a bound that says us that from an asymptotical point of view, the flooding time is always depends only on clearly n, the number of nodes, and the p, which is the edge birth rate. Okay? And very importantly, this means that when q is, say, constant, and p is something like 1 over c over n, if you replace p there, we have that function becomes logarithmic. So this means that we have a dynamic graph, an evolving graph, in which every snapshot is highly disconnected and diameter is infinite, okay? But the flooding time is logarithmic, it's very fast. And importantly enough, does not depend on the dead cooked rate, okay? So this is our first results about flooding on edge Markovian evolving graph. Okay, so what we can say is that the sparseness and high disconnectivity do not prevent fast information splitting, logarithmic information speed in edge Markovian evolving graph. Okay, so this model have been then used in several fields. Here just a list of fields in which this edge Markovian evolving graph have been used. And what is the next and the second part of our talk is, okay, let's start from spatial time dependency, but we want to introduce also spatial dependency, okay? And so what we consider node mobility. So we consider a region, maybe a square, two-dimensional square, and then we put n nodes, and then such nodes stars n independent random walks over this region, okay? Then we assign to each node a transmission radius and a move radius. The transmission radius determines, given two nodes, if the distance is within this transmission radius r, then they can communicate. And while the move radius rho is the maximal length of the random walk step. Okay, so if a node at any given time t is in a given position, then you take the disk of radius rho, and then its next position will be uniform over such disk and will be chosen uniformly over such disk, okay? And then you apply. So two nodes will be connected at any given time t if their distance is not larger than rho, and then the move radius instead determines the node mobility and the evolution of the graph. Okay, so this is just a figure. In this case, you see to every node v, the transmission radius is r, so such two nodes will have the edges because they are within distance r. while the raw disk, the red disk, does not determine the topology, determines which is the next position of node V at the next time, and will be uniform, chosen randomly uniform over all the disk. So at the next time step, we have that every node make a new move, a new walk, and one step of walk. So we have new position, but then we again apply the transmission radius, and we form the disk graph, the geometric graph at the next step. Clearly, we have two ingredients here. The fact that the topology at time t stochastically depends on the topology at times t minus 1, because of course it depends on the position of the nodes at the nest. But also there is spatial dependence between edges because there is geometry. So triangular inequalities holds, so you have also spatial dependency. Okay? And what we know about this model that have been often studied, frequently adopted in mobile networks. So we can again observe a sort of a threshold behavior. So if R is much smaller than square root of log n, then at every step the stationary distribution will be highly disconnected. Okay, sparse and highly disconnected. While if R is quite a bit larger than square root of log n, then we can say that the graph is strongly connected and has the diameter order of square root of n. In this case, there have been there were analytical results for the flooding time, and indeed what they prove is that the flooding time is sort of order of the diameter of the network, so something like square root of n. And but the analysis strongly exploits the fact that at every given time the graph snapshot was highly connected and had the diameter square root of n. So our next step is to consider a different scenario in which R is not only smaller than square root of log n, but is an absolute constant. So we consider devices that have only low transmission power. So if we look at the stationary distribution, we observe a very sparse graph and very disconnected graph, okay? But if the move radius, so the node speed, is enough large, so is larger than square root of log n, then flooding time becomes again optimal. So it's something like square root of n, which is the diameter of the region, over the speed, the maximal speed of the nodes, plus a logarithmic factor, which is in most cases negligible. So we observe that square root of n of rho in a region like this, if the edge length of the torus is square root of n, so the diameter of the region is square root of n, and you have a node that has velocity with speed rho, square root of n over rho is a lower bound, so you cannot get a better flooding time. And so we show that even though R is extremely small, the fact that the node moves randomly with the velocity rho, you get almost optimal flooding time. So the title of this paper in 2012-10 was something like random node mobility can make up for low transmission range. Okay, so if you have a mobile network in which you can assume a random and quite fast mobility, then you can use low range transmission and you get fast information spreading. Okay. How many time I have? 5 minutes? Okay. So I just want to say, okay, the random walk model is a very nice model, very simple model, but clearly we cannot say that is a realistic model for mobile networks, okay? So on one hand, it's often unrealistic, but on the positive side, it is quite far from trivial to study from an analytical point of view. And the technical issues that you have to cope with when you analyze it are very useful also when you want to analyze the same process over much more realistic models. And this is indeed the way the things for our next research. Indeed, what we did in 2010-12, we introduced a quite complex, we consider a quite complex mobility model, the Manhattan random way model. And this is something like that. So we have buildings and streets. So nodes start from a building, choose a random destination, then they must follow some Manhattan paths, and then they can exchange a message only when they meet each other. And by using the same arguments, but more refined and more complex that we derived, we introduced for the random walk model, we were able to to give almost tight bounds for the flooding time in this much more concrete case. Okay, so I have no time to introduce this third part, which is when instead not only the edge set change over time, but also the node set. I just give what we wanted to do according to this modular approach. We consider peer-to-peer network in which at every round, a random set of new nodes can join the network, following maybe a Poisson process. And then we also say that every node, the life of every node follows maybe an exponential distribution. So maybe in expectation we have that every node can, after n rounds, will leave the network. So you have a random set of vertices, and you have to decide also the topology. So when a node joins the network, just choose the random neighbors uniformly at random over the set of the vertices and try to connect it, okay? And these guys say yes, and then you connect. And what we were able to prove in this new game is that even if every node chooses only constant number of random neighbors, and even if the node char, so the frequency of changes in the node set is quite high, if the nodes are able to refresh quite often its neighbors, you can get not only fast information spreading, but also if you look at the topology at any time, is a good expander. Expander means that you have also a good fault tolerance. Okay, so let me conclude this talk. We studied broadcast dynamics in different model evolving graphs that gradually consider more and more concrete features by using a modular approach. We introduce one specific aspect. We see the impact of this aspect in the information spreading from a quantitative point of view. And then we use the proofs, the argument proofs, to go a step further to introduce another concrete aspects of dynamic graphs. And also we derive few k parameters like node speed or birth and death rate, and that are the k ingredient that determines the speed of information spreading. I conclude the talk, and if you have any question, I would be happy to answer. Thank you.